Hey everyone, and welcome to this explainer. Today we are going to completely shift your paradigm about how Kubernetes handles network traffic. Look, if you've ever spent hours, or let's be real, days, staring at routing tables or wondering why a specific service just won't connect properly inside your cluster, you are absolutely in the right place. We're going to strip away all those complex abstractions and track the exact physical journey of a single packet, right from the moment it hits the network cable, all the way to its final destination inside a pod. So let's dive right into this by starting with a deceptively simple question. It's one that actually trips up even seasoned DevOps engineers. When a network packet from an outside client, say someone trying to access your newly deployed web app, finally enters a Kubernetes node, who is actually processing it? Take a second and think about your own clusters. Who's the traffic cop here? Well, your first instinct is probably going to be to point to one of the usual suspects, right? Maybe you're thinking it's Proxy routing the service. Or maybe you think it's your container network interface, your CNI, like Calico or Cilium, managing that flow. Or hey, perhaps you think it's Kubernetes itself, orchestrating the network packets the exact same way it orchestrates your containers. But here's the reality check. It's literally none of them. Before a packet ever truly reaches a pod, honestly, before Kubernetes even registers that the packet exists, the Linux kernel is doing absolutely all of the heavy lifting. In fact, to truly understand Kubernetes networking, you actually have to understand Linux networking first. Here's our roadmap for today's explainer. We'll be looking at the K8 network illusion, the first hurdle with XDP, the core network stack, routing to the pod, the eBPF fast track, and finally, the true network protagonist. Section 1, the K8 network illusion. Let's start right at the physical entry point and burst the bubble on who is actually aware of this traffic. Imagine a packet from a client IP, let's say 192.168.1.100, is trying to reach a Kubernetes service. Our hero packet hits the physical hardware and has to follow these exact steps just to get recognized by the node. First, it travels through the physical network cable. Then it strikes the network interface card, or the NIC. From there, through direct memory access, it gets dropped directly into the computer's memory inside the RX ring buffer. And finally, the NIC driver actually picks it up. Okay, so the absolutely crucial point here is that even at this stage, when the NIC driver wakes up and tells the system, hey, a new packet just arrived, Kubernetes is completely and utterly clueless. All of these physical handoffs have happened, and the massive cluster orchestration system isn't even in the loop yet. Right now, it's strictly a private conversation between the hardware and the base operating system. Let's move on to Section 2. First hurdle, XDP. Now we run into XDP, which stands for Express Data Path. This is the absolute frontmost hook in the Linux operating system. It intercepts packets immediately after the NIC driver pulls them off the hardware, way before they ever hit the heavy, complex main Linux network stack. If you're running a modern CNI tool like Cilium, it's actually leveraging XDP right here to run high-speed access control lists and incredibly efficient DDoS protection. Depending on the security rules written into the eBPF programs running at this specific hook, our packet is going to face one of three fates. It could hit an XDP_drop command, which means malicious or unwanted traffic is just instantly trashed without wasting a single CPU cycle deeper in the system. It could hit XDP_pass, giving it the green light to keep going, or it could get hit with XDP_redirect, instantly bouncing it somewhere else. And here's the crazy part. Because XDP intercepts the packets so low in the system, right before the heavy net filter stack even wakes up, it can process mind-blowing volumes of traffic. We're talking tens of millions of packets per second, literally. This is exactly how modern infrastructure shrugs off massive network attacks without even breaking a sweat. Moving right along to Section 3, the core network stack. So, assuming our packet isn't malicious and gets that XDP pass, it finally enters the legendary Linux network stack. Now, the kernel rolls up its sleeves and does the hard work of parsing the Ethernet, IP, TCP, or UDP headers. Once it understands those headers, it transforms the packet into an SKB, or socket buffer. This SKB becomes the core object representing your packet, and from this precise moment forward, every single kernel module, whether it's IP tables, routing, or contract, is going to manipulate this specific SKB object. Next up, the SCUB hits the TC, or traffic control hook. Now, historically, this was just used for basic quality of service, traffic shaping, rate limiting, that kind of stuff. But eBPF has totally flipped this on its head. The TC hook has evolved into a massive integration point for advanced networking. It now handles complex security policies, load balancing, network address translation, and service discovery. It's right here at the TC hook where we finally start seeing the real influence of your Kubernetes routing logic actually taking shape. Section 4. Routing to the pod. Okay, our packet has passed the security checks, it's shaped up properly, but it still has to find its actual pod destination. In legacy Kubernetes networking, the packet now enters the netfilter pre-routing hook. Let's say its original target was a Kubernetes service IP, something like 1096.0.100. At this exact second, all those thousands of IP tables rules generated by kubeproxy kick into high gear. They trigger destination NAT, or DNAT. Suddenly, that service IP gets translated and overwritten with the actual physical pod IP address, like 10.244.1.20. You know, this is usually a massive aha moment for anyone learning cluster architecture. Your Kubernetes services, they don't actually exist, not as tangible network entities anyway. They are practically just an illusion, a super convenient abstraction, created entirely by Linux IP tables, constantly rewriting packet destinations under the hood. Kind of wild, right? So after all those routing decisions are finalized by the kernel, the packet still needs a way to physically cross over from the host machine into your isolated container. It does this by traveling through a VETH pair. Think of it as a virtual Ethernet cable. On the host network side, acting as one end of the pipe, you've got something like VETH 1234. On the other end, connected securely inside the pod's isolated network namespace, is the F0 interface. Our packet flows through this virtual pipe, and finally, the application inside your pod receives the data. Section 5. The eBPF fast track. Now, that entire path we just walked through, that's the traditional way. But compare that traditional path to this modern paradigm shift. Traditionally, a packet gets dragged through an absolute maze of IP tables, connection tracking, and NAT translations before it ever sees a pod. Sure, it's reliable, but as your cluster scales up to thousands of services, evaluating those massive lists of rules sequentially becomes a huge bottleneck. But if you implement eBPF with a tool like Cilium, we completely bypass hundreds of thousands of those slow rules. The packet enters, a near-instant eBPF map lookup happens, policies are checked right in memory, and boom, it's routed straight to the pod. It's doing all that heavy lifting directly in high-speed programmable kernel space. Section 6. The True Network Protagonist. Let's pull all of this together to reveal the true hero of the story, the real engine making your infrastructure hum. This is the modern, highly optimized packet journey. It goes from the physical NIC directly to the XDP hook for an instant security check, then into the TC eBPF hook where service lookups and complex policies are resolved instantly via map lookups, straight through the virtual Ethernet pair and right into your pod. This totally streamlined path proves exactly why massive, enterprise-scale Kubernetes platforms are rapidly abandoning legacy systems and moving to a zero IP tables architecture. It's faster, it's way more secure, and it's infinitely more scalable. Which brings us to our final big takeaway for today. Kubernetes doesn't actually forward packets. The Linux kernel is the true protagonist of this whole story. Kubernetes is essentially just a very, very complicated control plane that tells Linux what its intent is. So next time you are pulling your hair out troubleshooting strange cluster traffic or a randomly dropped connection, ask yourself, are you actually debugging Kubernetes, or are you really just debugging the Linux kernel? I'll leave you to ponder that one. Thanks for joining me on this explainer, and keep exploring the systems running beneath your code.